It's like, oh my gosh. Whoa. Okay, sorry. Can you hear me? Yeah, it's good. All right. So, okay, let me just. Okay, so we decided, like in the last session today, Peter and I, to give you some survey of the stuff we are doing here. A shorter talk, probably like 20, 25 minutes. And so I decided to pick something that should be relatively broadly understood. A kind of everyone should get something out of this. So this is a joint work with Veselin, who is a PhD student of mine, and Manu Sridharan, who is a who is a researcher at IBM Watson. So the basic problem that we're looking at is this concurrency analysis of event-driven applications, right? So, for instance, CNN, web pages, mobile phones, and all kinds of devices like this. So this is an important domain. Lots of such applications. Each of these websites is essentially an event-driven application, right? So I got this picture from Bill Gates where he said, like, Control Alt Delete is a mistake. So I don't know if it's true, but we'll see. And so we kind of focused on this domain, and we were interested to see what are kind of the correctness issues that arise here. Okay. So these event-driven applications are structured in a particular way. So essentially, the application is structured in a way which responds to events. Right? So all kinds of events, network events, user events, application-generated events, and so on. Okay? Sorry? 1 trillion web pages. I mean, yeah, I think it's web pages. Yeah, maybe it's like each web page, each website may have many web pages. Yeah, so this is constantly growing, right? Right. So, okay, so that's why we are interested. We are interested what are the correctness issues that arise here, and we're interested. So I'll show a few things in this talk, right? I'll show you some of the concurrency issues that take place, and then I'll show you a demo that we built, like a nice tool. Veselin built a nice tool, and so you can go to this website here, EventRacer.org, and try your website. Okay, so there is quite elaborate analysis going on the back end here, which I'll talk a bit now. All right. So we'll get to the demo later, but so one of the main differentiating characteristics for this type of applications is the fact that you want really fast response times, right? When you click on something, you want to get a response back. When a network network packet arrives, you want it to be processed quickly. Okay, so what tends to happen in many of these applications? So if you look at something like CNN or something like an Android phone, there is quite a lot of asynchrony going on. Okay, there's a lot of concurrency going on, a very complex control flow because of the event-driven applications typically have quite a complex control flow. So there's a lot of asynchrony going on here, although it's not explicitly spelled out in the application, right? You will not see something like in Java, like fork, join, thread start, or any of this. So it's we'll see what kind of problems this leads to, kind of unexpected issues. So this is actually a problem that problems caused by this asynchrony that was mentioned to us about a couple of years ago by one of the main designers of Firefox, who said that their tests were like crashing non-deterministically, and they didn't like this. So let me give you an example of what happens, okay? So of non-determinism that can happen due to the asynchrony. So this is a web page, okay? So web page starts, then there is some JavaScript that is running here, and there is like a variable called gates, says gate is great. And then there is an image here, right? So there is an image here, and when the image is loaded, it will be the gates will be set to poor. It's an event handler, okay? And here there is another image here, and if this thing, when it gets loaded, this image, there's going to be an event handler executed, which shows on the screen what the value of the gates variable is. So what do you think this should give as an output on the screen? Either or, okay? Depending on the way that the requests get arrive. So if you start running the application, right, the browser is essentially interpreting your program. So it says gets to great, sends a request for the image, sends for a second image. If the second one arrives first, it will set the variable to great and show this. Otherwise, if the first one arrives first, it will execute the event handler, and then you're going to see this. Okay? So depending on the order in which the images are loaded into the browser, you get different results. Okay? So that's one example of the non-determinism that happens in this kind of applications. Okay? And so there is a bunch of examples. I think there was an example of like Hotmail losing a bunch of mails a while back due to this kind of problems. All right? So here's another one. Non-determinism happens due to user interaction. So what can happen here is you have a web page, and here you have a button, and there is an event handler that gets executed whenever the button is clicked. So when you click the button, it's going to call this function here. And so if you have the execution here where the browser parses the button and shows it on the screen, and then the user clicks the button, it's going to crash the program, right? Because this function f is not yet resolved here, not defined. Okay? So you can get things like this, and it's especially annoying if you're on slow connections. Sometimes it happened to me. The page is loading slowly. You click something, nothing happens. The page breaks, and so on. Right. So the bottom line out of this, from our point of view, is that this asynchrony that is in this type of application causes non-determinism. So unexpected non-determinism that you kind of users may not expect. Okay. And one observation here is that you can look at these behaviors essentially. I'll call them data races. You can call them concurrency bugs. You can call them many things. We're just using this term data races just so people are familiar with this. But the bottom line is that this non-determinism causes this kind of concurrent interference, okay? And so once you see the problem as it's causing data races, then the question is, can you detect these things and then fix them and so on? Okay, so despite the fact that these applications are executed by single thread, you have a thread, pick something from a queue, from the event queue, then execute, then pick something else and execute, you still get this kind of non-determinism. So essentially, for the purposes of analysis, if you try to model these applications as event-driven with an event queue, you kind of miss the point of how actually this concurrency can happen. So this is the way that it's implemented, but not the way that you could get the traces of the program. You get arbitrary orders. Okay, so for the purposes of analysis, we're interested whether we can actually analyze these pages, analyze this application, and detect these concurrency bugs. That's what we're interested here. Okay, so this is a template for concurrency analysis, okay? So if you open any paper, this is what you'll see. Not just race detection, any concurrency analysis, static or dynamic. So you basically see a program as input, you have a happens before model, and John talked about a bit. And then you have some notion of location, where interference can happen, okay? This can be like a physical variable, it could actually be a logical location. For instance, commutativity violations. But these are the general ingredients that you have. And then you fit those into the analysis, and the analysis tells you here are the bugs here's the races that you get, okay? So this is very worked out. For languages like Java, you have a Java program that happens before model is clear. You have fork join, it's a very direct model here. And the memory locations are typically primitive locations, like shared variable locations and things like this. Okay, so for the web, before you start looking at this problem, it was basically this situation, right? You have a page, and you don't know what this is, you don't know what any of these things are. Okay, so the most natural question is, you say, okay, I don't want to invent anything, I just want to reuse what's out there. There's been like 30 years of work on this, okay? So I just want to just give me these two pieces here for the web or Android, it doesn't matter. Give me these two pieces, and I'll just reuse the existing analysis, and then I'm done. So you just try to reuse as much of the existing machinery that's possible. Okay? And so the first thing to do here, if you want to analyze these things, is to say what is the happens before for, say, the websites and web pages, what are the memory locations. So I'll go over those quickly because this is quite tedious. But for memory locations on a website, you'd get things like JavaScript variables, functions, HTML DOM elements, event targets, handles, and all kinds of things. So getting these memory locations is a fairly elaborate process. It's, you have to go over the HTML5 specification. It's quite laborious. The next thing that you need, once you get where interference can happen, is to define what is the notion of an atomic action, right? So for something like Java, an atomic action is just the execution of a single statement, shared statement, and then this is your atomic action, and the happens before is between those actions. Here you have to define the notion of atomic actions. So for instance, an atomic action is parsing a single HTML element. This is what I showed you, or the execution of a script, or processing an event handler. Event handler execute atomically. So once you define what's an atomic action, you have to define what is the happens before relation, and this happens before relation is built between these actions. Okay? So how do you build the happens before relation? What should be ordered before what? That's a very important question, otherwise you cannot do the analysis. So this is a problem that comes up in like bigger application, what's the happens before relation. If you're trying to analyze like low-level algorithms, I don't know, like bakery or something, there everything can happen with anything in parallel, so there's no such problem. Okay, so this is quite laborious to define, okay? We spend like quite a bit of time here. So just the hacking factor here is huge. Because this was not defined before. You have to open the HTML5 and really understand what can go before what. There are browser differences, so you have to look at what they do. But at the end, we came up with something. So there's a paper on this that discusses this happens before. Okay, so just a quick example. The same example as before. Here are the event actions, and we are going to here's the actions. Of atomic actions over which we are going to be ordering. So there is going to be ordering between this and this one. This happens before this. Parsing of the execution of the script happens before parsing the image, and the execution of this event handler happens after parsing the image, and so on. So if you build the happens before for this example, you would get something like this. Okay. So the happens before tells you the arrows means that this happens before this, and when it's not ordered means they can happen concurrently. So that's what the happens before looks for this example. Okay. So once you have the memory locations and you have the happens before, you should be done. Okay. You should just take an existing analysis and just run it, and that should be it. Okay. So it should be very, very direct. So for this particular work, we will look at dynamic analysis for some of the reasons that Jan mentioned, and also these are really, really large websites with dynamic evaluation and all kinds of things. And so we said, let's look at dynamic analysis and let's just run existing analysis, get this thing over with, and just move on. Okay? The problem is, if you pick any existing concurrency analysis, any of them, you're going to have into huge troubles. Okay? So the two huge troubles are, and this starts the part of the talk where these techniques that I'm presenting they have broad applicability, they're motivated by the looking at these websites, but really they are applicable to any analysis. So the first problem is that there is a problem of precision, okay? You report too many races. So on something like CNN, I'll run it for you now, you may get like 10,000 races, okay? Just from like 10 seconds run, okay? The second problem is that they don't terminate, essentially meaning that they run out of space. So the vector clocks or whatever data structure they're using, it just takes too much space, and they just don't finish. So if they finish, they're imprecise, and they sometimes don't finish at all. It takes forever. So these are the two problems that we want to solve. Okay. So how do you solve these problems? So the first one I'll show you is this precision problem. And I think that some of the insights, we cannot realize it after writing the paper, is actually a quite general problem of how you go about this. So let me show you an example. That's the best way to go about this. So here I have a simple web page, and on this web page I have free shared variables. Okay, so the free shared variables here are this init, this y, and this y.g. So y is constructed here, and g is this is an object, and g is a field of that object. That's what you have. Okay. And so, if you run a standard detector on this website with the happens before model that we built and the memory locations, it's going to give you these three variables as races. And even though this init variable here, this accesses to init here and over here, are really preventing you from having races on the remaining two variables y and y.g. So you cannot have races. Because this init here, this can only get inside after the init has happened, but the y is before the init. Okay? So you cannot get a race here, only on the variable init. All right? So what you'd like to do intuitively is to only report the races that can really happen. So you want to report only the races on the variable init, but not on the variables y and y.g. So of course we can look at why you could get a race on the variable init. It's because once you parse this stuff here, there is the button here, and then there is the script here. So once you parse the script, this can get parsed, and then somebody can click it and execute init, or the other way around. Somebody can click on this before this is parsed, and then this thing would set init. Okay, this is ideally what you want to do. Okay, you want to report only things that are guaranteed to exist. Okay. So I'll be like, it's like same formal here, just trying to get the intuition across what happens. Okay. So what do you mean that the race is guaranteed to exist? Okay. So very informally, it says that it's guaranteed to exist if there are two traces who are in the actions in that participating in the race. So C and D are the two actions that are racing. So this C and D. Then it's a real race if I can reverse the order. So there are two traces. In one trace it's CD, and the other one is DC. Okay. So for this particular example, right? You have the race CD is guaranteed, but the races here B, and this race B and A, this race BA actually cannot happen. All right. Okay. So one thing you can do. So let's be precise here. So one thing you can do here, if you want to solve this problem of reporting only the real races, one thing you can do is naively just record the whole dynamic trace if you're doing dynamic analysis, and then somehow start looking at the dependencies between yj init, start to doing this kind of stuff, and figure out somehow that y.j depends on init, and then I'm just going to report init. Okay? This is not what happens in practice, because if you try to record absolutely the whole trace, this is very expensive. This is like all the primitive operations, all the conditionals, everything. So this is expensive to do. So what tends to happen is, what you do is you record an abstraction of the trace. So you don't record the full trace, you record an abstraction of that trace. And what you abstract away is all this, everything that is not a shared access. So if I had like a bunch of here, I don't know, local operations here, I would not record any of this. Any of the conditionals I would not record. So I may see something like this in my trace. A, action A, read Y, and C, write init. So just the writing to init, and here I read from init, and here I read from y.g. This is what I may see in my trace. Right? So this is already an abstraction of this trace. So now, when you ask the question on this kind of abstracted trace, how you figure out races that are guaranteed to exist? I don't have the original trace anymore, I have the abstracted trace. So that's one question that comes up. And just scroll down. So you can imagine even a more abstracted trace. I have a dynamic trace, and here I can tell you that I don't even know what those things are inside. I just tell you that there is a race. That's all I tell you. So I take my program, I record not the full trace, but some abstraction of the trace. There could be many different abstractions you can record, and then I can ask you on these abstracted traces, what are the real races, okay? And why would you do that? Because it's very expensive to record the whole trace completely, and it's expensive to check this to figure out the real races. So I record an abstraction. Okay. Now what happens is, you ask these questions, what are the races guaranteed to exist? Okay. And if you ask yourself this question, so what should I do? I have the abstracted trace. What is absolutely guaranteed to exist? So before I even compute these things in the abstract, I can say that a race like CD is guaranteed to exist if for any concretization of this abstract trace, that race exists in all the concretized traces. Okay? So I take an abstract trace and I say for any concretization, this must exist in these concretized traces. So let's not talk about like what it means for a race to exist in a concrete trace. There is a formal definition of this. But the central thing here is that there is very clear definition of checking things in the abstract. You concretize it to the concrete and you just check the property there. But the problem is you cannot concretize this abstract trace to the concrete. There is an infinite number of those, because there is an infinite number of ways I can fill these things in between here. And in many ways I can fill this. For instance, I don't know if these are between write-write race or read-write race. I may not know this. I just know there is a race. Okay? And so this question, how do you answer this question, okay? And so here is the declarative thing that you want to have. What you want to have is this theorem which says if I would define some definition of a race at the abstract level, such that if I tell you there is a race at the abstract level, this is a guaranteed race. Okay? So if I tell you there is a race at the abstract level, this means that there is a guaranteed race for sure. Okay? So in theory, this means that the definition for R is determined already from the theorem that I want and from the abstraction of the trace that I picked. In this particular work, we instantiate it with a particular definition. So once you define a particular definition at the abstract that you're checking in the abstract, this definition, so this theorem holds for this definition. But in principle, I can change the abstraction of what I'm recording, what partial observability I have from my program, and this will change this definition here. Because my theorem doesn't change, this thing there doesn't change, the only thing that changes is this definition. Okay, so that is something that is not, that hasn't been looked at really at all, kind of in this analysis field. And really, maybe we shouldn't even call standard race detectors like race detectors because they report so many false positives. If you try to report the real races, then you need to do something else. Okay, so this is the theorem. So we're going to define this notion of uncovered races, and if I check this in the abstract trace, then for sure I have a real race. If I find an uncovered trace, okay? Good. So I want to find uncovered traces. That's what I want to do. Uncovered traces means this is a real race. It exists under any interpretation of the trace that I recorded. My program that I had, that I recorded the trace from, may not actually, under my program, this actually may not, under my program, this is also a real race. So under any program that I have, this is a real race, including my program. So the key thing here is, I take my program, I record the trace of the program, an abstract trace, some things are omitted, and then I have a definition what I'm checking on this. So I want this uncovered traces. I want to find those. So I need an algorithm for those. Okay. So in terms of precision, right? This is one of the things that really helps, where you are trying to report only races that are guaranteed to exist, nothing else. Okay. Now, if you are doing any kind of race detection, you basically have to compute reachability. Okay. So this happens before relation that we define. It's essentially a binary relation. And one of the observations is that if you represent the binary relation as you can represent as a directed acyclic graph, then you can ask whether two actions actually participate in a race, but just checking reachability in this graph that represents the happens before. So for instance, if I have this happens before graph, I have A, B, C, D. These are my actions. So I don't know, this is like parsing a script, or this is executing an event handler. This is doing something else. Then the happens before here is the B is before D is before E, and so on, okay? So if I want to know whether I have a race, I can just query the graph. So I can say, is B reachable from C, is C reachable from B, and so on, okay? So once you take your trace and you build a happens before relation and you represent it as an acyclic graph, you can just run your favorite graph, your reachability algorithm. Okay, so I'll show you like few algorithms. And the first algorithm that we tried, BFS, the most naive algorithm, this is the space and time complexity. It doesn't do any precomputation. It just takes the graph and runs this. So this doesn't work in practice, okay? The problem is that these graphs inside like a web page tend to be on the range of hundreds of thousands of nodes, even for small test harnesses. So the next thing that you can do, and you can observe this actually hasn't been, it's not phrased like this if you read the paper on race detection, but what they're doing really, we've observed, is essentially doing reachability with vector clocks. So what they do is they take this graph, all the elements of the happens before, and they assign vector clocks to them. So these are tuples here, these bits here, they assign these things. So this is just a map from a node to a natural number. So for each of these things, there is a map at each. So for each, so I have here 1, 2, 3, 5. So the length of the width of this thing is 5. So for each event in the graph, I am keeping a value here, and this is kept at each node in the graph. This is what state-of-the-art race detector do, except they do it online, but it doesn't matter. So this is what they do. And then reachability here, if you want to know whether there is a path from B and C, I just compare the vector clocks. So for instance, the vector clocks of A and the vector clock of D is here. And so D is after A because this tuple here is included inside this tuple here. But the B and C participate in a race because the vector clocks are non-comparable. So what it does, takes the graph, computes the vector clocks, and then queries the vector clocks, okay? So that's all it does. That's state-of-the-art race detection. Okay, so this is the pre-computation time. You have the graph. If you do a pre-computation time to compute the vector clocks, this is the complexity, and the query time is constant. Okay? So if you try this thing, this also doesn't work. Okay? And it doesn't work because the space complexity is extremely high. It's n squared. So if you have a graph with 100,000 nodes, you get 100,000 to the 100,000 elements. So this also doesn't work. There is a paper in the 1990s, like many things in computer science, like were looked at in the database community. So there is a beautiful paper by Jagadish from 1990, which talks about the technique of essentially partitioning the graph into chains. Okay? So the basic idea, if you look at this graph here, is that we are going to rediscover what are the threads of the program by partitioning the graph into equivalence class. So basically, you're going to partition this graph here into different chains, and then you're going to work with those chains. So this is what his algorithm does. Okay? So the algorithm, for every node in the graph, computes a chain to which the node belongs to. Okay? And so for this graph, we could partition it by having two chains. A and B belong to this chain. C, D, and E belong to the blue chain. There is another chain also. You could have had A, C belong to another chain, to one chain, and B, D, and E belong to another chain. Okay? So there are different ways you can partition the graph. So Jagadish algorithm for partitioning the graph, the partitioning part is all n to the third plus C times m when C is the number of chains. Okay? So once you take your graph that you have that happens before, you partition it into these chains, then you can use the vector clocks on this graph. So this is the chain computation time, this is the computation time for the vector clocks, and the query time is constant, okay? The good thing is that the space complexity improved. It was n squared, now it's C times n. C where C is the number of chains. We actually use a greedy version of this, where we are not guaranteed to compute the optimal number of chains, but it works fairly well in practice. And here the chain computation time is C, where C is the number of chains, times M, where M is the number of edges. Okay? So this is the algorithm that actually runs. Okay? So just to recap here, so if you try to apply traditional vector clock-based race detectors, like fast track and others, this doesn't work. Okay? You're just not going to terminate. You have to do something else. So this is the basic idea, right? So you define the happens before, you define the memory locations, and here you have to do some combination of techniques. Vector clock is a known technique. Race coverage is something we introduced. It was also studied in the late 80s by Netzer. And then a lot of the weak memory model work came from his papers. And then we use Jagadish's chain decomposition of the graph. So when you combine these things, you get an algorithm that actually works. Okay? So our contribution here is in combining the things and maybe in the greedy computation of the chains. Okay, so now I want to show you the demo, and I'll go to the website where all this stuff is implemented, all this stuff works. So I'll go to some website, I don't know where. You can tell me what website you want. My homepage, that's not fair. Fox News, huh? No, there is ETH, we can go. So ETH, so you can run this, and what this thing is going to do is going to analyze the web page, and it's going to essentially run the race detector with a bunch of different inputs. Okay? So it takes about 20 seconds, so this works on the cloud, and runs all these algorithms that I just showed you, computes uncovered race, and so on. So let's see what happened here. You click to view races. Oops, I clicked, I think, the wrong, wait a second. What did I click? Well, no, I screwed up something in running it. 1 second. Well, let me try this one. How about Gmaps? Was it HTTPS? Okay. I don't know what happens with Gmaps. So this is like without demos, it never works in the. But you can go on the website, you can try it, and you can give feedback. It takes about 20 seconds to analyze the page, and then you can see. I don't know what happened. I don't know if it's. Oh, I think something is broken. What?
There must have been a race.
There maybe is a race in the code. So I don't know why it doesn't work here. Wait, let me see CNN. I can go to CNN. I just ran before. Doesn't matter. Okay, so I will leave it to run now. And actually, I know what may be the problem. Wait a second. So www.cnn. Sometimes it behaves. Okay, fine. So let's leave it to run. And we will. It says the demo is quite robust. Yeah. Hey, it's quite robust when it matters. When it doesn't matter. So CNN. I don't know. Okay. So now it works. I think I typed something. Okay. So I analyze CNN. Okay. So I analyze the whole CNN. So okay. So what this shows you here is all the uncovered traces. This is the concept that I showed you. Okay. So this is all the uncovered traces. If I click all the races that the normal detector would report, it would be more races here. So for instance, you'd get 28 traces. In some websites like Gmaps, you may get like, I don't know, 50,000 if you keep running more and more. So here are the races. Okay, the tool gives you this. These are all the uncovered traces. These are races that are guaranteed to exist. So this is especially high risk. So you can go to this race and you can start to explore it and to look at what actually is happening. So this gives you the happens before of the race. Tells you exactly between what and what it is. You can look into the JavaScript here. So this gets quite complicated. So this is the CNN JavaScript. And so on. You can explore these races. You can explore this race like this. There's actually a bug on the ETH website that is found. Okay. So all right. So there is this EventRacer. So there was like some interest of this from like Netflix, Google, and those places because they just want to feed their website through this and then just see if there is any kind of asynchronous issues. So there was one issue actually. Vesco, correct me if I'm wrong, but there was like one issue where in Google Maps you focus on something and then you go to Antarctica or somewhere because of such a problem. Okay. So we ran this analysis in a bunch of Fortune 100 websites. The most interesting part, I think, is probably here. If you run classic graph connectivity, so these are the graph connectivity algorithms. We're not even going to run BFS because we ran it, but it's just hopeless. So this is vector clocks without chain decomposition. This is like the standard race detection, right? So when it terminates, the mean is like it takes about 540 megabytes, and the maximum is about 25 gigabytes. Versus the chain decomposition. So it's quite, this performs relatively well. Okay. There's a bunch of harmful races that it found, broken functionality in these Fortune 100 websites, like missing analytics. So the analytics is broken. So the information you get from the website is actually broken. The UIs didn't work, and a bunch of other problems. So there's a bunch of like different things that this kind of work kind of opens up, and so this thing that I said about this race detection, about how you actually produce the real races, this is actually a deeper problem that we don't yet quite understand it, I think, in depth. There is some other work here. One very common thing in this web framework is that you almost very frequently you have races that are not between the low-level reads and writes, but between high-level operations. So with Eric Koski and some other people, we are working on generalizing this to commutativity and so on. Okay, so I think that this is it. Try it out and see if it works for you. Okay, thank you. Yeah.
So my understanding was one of the reasons for the problem is your browser
process starts loading a page, and before it loads, everything is starts executing your Java, and you can only click on something and cause an event.
That's like one issue that we have.
So maybe a cheat fix would be first finish executing and then allow these events.
Yeah, so there is like a bunch of websites. If you Google for this problem, there's like a bunch of people. There's actually a book that's called Async JavaScript that came out last year, and a bunch of blogs where people are like, here's the text that you do to get fast page loading. So enable things to load quickly, and there's lots of this going on. So they don't do that. They don't like load the whole page and then you click that button. Yeah. Yeah, this is a very good question. So you can get false negatives. So even in a dynamic run, you could get false negatives by saying that, so these uncovered races that we compute, these are real races, but the races that are covered, some of them may actually also be real races. But because it's in the abstract, we don't know. It's like you're in the abstract. So if I say a race is covered, we're not going to report it. It's still there, you can exploit it, but we are basically saying this race is covered. So this could be a false negative. It could be that this race actually was real. That's one way you can get false negatives. In our, we looked at many of these races, and typically many of them indeed turn out to be covered, but it could be that that's not the case. This is just, I think under this abstraction, where you just record shared reads and writes, this is, in fact, I think we can prove this is the best you can do. It's impossible to get anything better.
Okay, but we're already running 20 minutes late, so let's start the discussion again and thank Martin again.